Alright, so we talk about Chapter 10 today. Sorting and searching algorithms. So we're gonna look at how to sort and look at the efficiency of each sort type in terms of big O. So we have simple sorts, we have big O of n log n sorts, and then we can look at searching and hashing using hashing function. So putting an unsorted list of data elements into order, that's what we call sorting, and this is very useful operation. We describe efficiency by letting the number of comparisons to the number of elements in the list. So to help us test our sorting algorithms, we create an application called sorts. So the class defines array values that can hold 50 integers and static methods init values to initialize the values of an array with random numbers between 0 and 99. And each sorted returns a Boolean value indicating whether the values array is currently sorted. Swaps the integers between values at index 1 and 2, where index 1 and index 2 are parameters of the method. And then we print the values out. So look at our main program using swaps. So first we initial values, print the values out, which is unsorted, and we start to do swap. And normally at this point we want to put the sorting algorithms here and then print the values back, then it's going to be sorted afterward. So this is an example of sorted output. Now the outputs of an array is not sorted. When we talk about print out here, right, you see the value is not sorted, it's say false. And again, after we swap from index 0 and 1, you see it's just switching between two values, and it's still not sorted at index 0 and index 1. Now that's why we need to put the sorting algorithms here, right, instead of swap. But part of sorting we need to swap. Now let's look at the simple sort, selection sort, bubble sort, insertion sort. So those are the simple sorts. Selection sort is like you select, right, the name that comes first. If you want to sort the name of the people alphabetically order and write on a second sheet of paper. So just have two sheets. One is the list, another one is empty sheet of paper. So pick the one starting with A first to go on the new sheet, and then you cross the name out on the original sheet and keep repeating that until you get a sorted list. Just look like that. So improvement, we see that algorithm is simple. It requires space to store two complete lists, so that's a drawback. So instead of writing the first name onto a separate sheet of paper, we can actually exchange it with the name in the first location. So that's why we need swap. Like in the same sheet, we see Hemming has to go first. So we swap Hemming with Perlis. And then we keep doing. We see McCarthy go after that. So we swap the second position, which is Wilkes, and McCarthy go there. Keep doing that. Next is going to be Minsky, and Paris is getting swap again. And then the list will be sorted at the end. So look at selection sort algorithms. So we can look at starting from loop from 0 to size minus 2. Why we're minus 2? Because first minus 1 because it starts from index 0. Second, we have to minus again because we don't have to sort the last item on the list. Okay, it's just by itself, we don't have to sort it. So that's why minus 2. And first, what we need to do is find the index of the array that hold the smallest values and swap the current elements with the smallest unsorted one. And just go through that with a loop. For example, we want to sort the numbers. So our current index is 126. Go to the list, we found the smallest one. We swap 1 and 126. Then the second current value is index 1. We go to the list, 26 and 43. Go to the list again, the second current value is now 43, index 2, which is already min. Then we don't have to swap. Stay where it is. Go to the list again, 126 and 113, 113 swap. And then we're done. That's why we minus size minus 2. Like this is 5 minus 2, right? 1, 2, 3, 4, 5. So we only do 3, right? It's 3 actually is start from index 0. So that's why it's 4, 0, 1. At index 0, at index 1, at index 2, and at index 3. Okay, and we don't need to compare the last one because it's sorted in the list. So look at the snapshot. If the list is big like that, we say the current is going to keep moving down, right? And size minus 1 is the index of the last. When the blue part is when it keep moving down, the blue part getting sorted, and the white part is pretty much just the one that is unsorted part. And we can see that the value in sorted part always going to be less than equals to the values of the unsorted part. Now this is how we implemented after we decided algorithms. Min index, right? So pass in start index and end index. And we initialized min index equals to the start index. Right? We assume that the first one is min. and we try to iterate the loop, right? Starting from the start index plus 1, right? The next elements from the current index. We don't need to start to index itself because we try to find the next one, which is comparing to the current index if it's smaller or not. So if it is smaller, then we set index of min equals to the new index because we find a new min. So we return index of min. So this is pretty much just a method to find min index. Right, we do that into the end of the index of the list because we have to reach the end of the values. Now, the selection sort itself is actually here, where we say we start from n index equals to size minus 1, and the current equals to 0. We iterate to the end. We start to swap the current to the min index. Okay. So let's look at what the function swap does. So this is swap. Swap pretty much just pass index 1 and index 2 in, and get the values of index 1 put into temp, and then replacing the values of index 1 with index 2 values, and now put the temp back into index 2 values. So that's how we swap, by just switching, right, the values. Now this one, it looks like it's going to go through and keep swapping if, right, it's always going to return index of min. So even it's not reaching the if the current index itself is min, it's also return the current itself and swap to itself. You may see this algorithm is also doing that. So that's why it's still sorted, but it's just kind of redundancy a little bit here. Like it still have to swap itself. But that is what we look at this. Even we found 43 is the min, which is the same as current. It look at cell and put cell back. Okay, so this is the selection sort, and once we run the program we call selection sort, now the list will be sorted. Now let's look at the analysis of big O. Look at efficiencies. We said we describe the number of comparison as a function of the number of elements in the array, which is the size as the n. Min index is n minus 1 times. So when we try to find min index, so it's going to cost about n minus 1 times, right? And within the min index, the number of comparison varies. The first call there are n minus 1 comparison. The next call there are n minus 2 comparison, and so on until the last one is 1. Right? Because you have to compare every time. So the total number of comparison is going to be adding up until 1. And from here, this is a series which is equals to n times n minus 1 divided by 2 arithmetic series. So we can see this is about n square efficiencies for selection sort.